Hello. So today we'll discuss on how to scale LLM Inference with vLLM. So we'll discuss on how to scale with multiple accelerators, and also how you can extend, how you can scale inference on large platforms. So first set quick introduction. So I'm Erwan Gallen, product manager in Red Hat. I'm following everything hardware accelerators on inference for the Red Hat AI product. So we are providing MLOps platforms. We are also called OpenShift AI, or also providing platform for model alignment. And we are working a lot with PyTorch, so it's why we are here today. And my colleague Eldar.
Hello everyone, my name is Eldar. I work as a researcher at Red Hat and the Institute of Science and Technology of Austria, and I mostly deal with quantization inside vLLM.
Good, so you are mostly all here because the world had changed in 2022. So Matt was kicking off open source in the introducing keynote. And when OpenAI has launched ChatGPT, all the world has focused on GenAI and has started to understand what is GenAI, but also for the company and all the open source communities, this model of OpenAI disrupting with extending the dataset size, extending the number of parameters, it was like a huge wall on the proprietary system, the central system, were like impossible to compete with open source. But with the power of open and also all the community, all the contributions, so in 2022 we had no open source models, so like impossible to compete with any proprietary models. But Meta with Llama has started to introduce, so also the team in Paris of Meta has contributed to this, launching open source. And also, we've also another French team from Mistral. All the models have started to be better in the benchmark. And today, if we look also on this conference, we talked about DeepSeek. Now there has been an explosion of capabilities for open source, and now the standard is to use open source. And in these models, so Meta Llama can beat with the best with Cloud Sonnet on DeepSeek. We've also a huge use of platforms, open platforms. So PyTorch is the foundation for this platform, but also vLLM has emerged. So Hugging Face has created TGI that was used a lot at the beginning, and vLLM is starting to emerge as the de facto standard for inference platform. So it provides advanced algorithm for IQPS, and you can start from a single server through a large-scale deployment for data center, so it can fit any use case. And also at the beginning of LLMs, TensorRT LLM engine was limiting the performance of all open source as it was for the models, and now it can compete with TensorRT LLM. So it's really the comparison point for any alternative methods. So it's easy to use. So with vLLM, you can just download, and it's crazy the number of downloads. So we have reached an average of 100,000 downloads per day. On some days, I think last month it was 300,000 downloads per day. So it's with the Python libraries too. And so it's really the standard used by everybody, and also the place where all the company can contribute and can collaborate together. If you look at the launch of Llama 4, day one, Llama 4 was supported. So it's why in the community we work and we receive sometimes from 10 days before any model. Like a model cannot be released without being in vLLM. And also it provides an OpenAI compatible API, so it's also easy to integrate with agentic or integrate also with existing platform. And Red Hat also is a core contributor of vLLM, so we have acquired Neural Magic was one of early contributor of vLLM, and the project was created by UC Berkeley, and now we are the first contributor of vLLM. So one of the key strengths of vLLM is integration with multiple accelerators. So it's also helping for the scale, not limited to one specific technology. So with vLLM, you can run any model, but also any accelerator. So we have different level of maturity for these accelerators. But really, it's the openness and the contribution of a lot of companies, a lot of accelerator vendors. So with a key integration of NVIDIA GPU, and recently with 0.8 integration of AMD GPU. Recently at Google Next on stage, one of our colleagues has announced it's a contribution of Red Hat, the support also of Google TPU integrated in vLLM. And many others are coming. The project has evolved with a plugin mechanism to easily integrate new accelerator, and you have some core accelerators on multiple accelerators. So how to scale with vLLM? So as a user, you can play with your laptop, you can use cloud, you can have your own servers, but with a recent model, it's really difficult, and one model does not fit in one GPU. So it's why we discuss of the techniques on quantization, but also how to scale from single device, moving to a single host with multiple device, to multiple host, multiple device. So we say device, but it's mainly GPUs for now. And for each of this scenario, vLLM can scale and can provide also increase the compute, the VRAM, and also the capacity. But so when you will scale with multiple device, multiple hosts, you will have also more hardware requirements. Speaking of the interconnect between the GPU or RDMA across the node. So scaling is requiring additional capabilities on your platform. So first, moving from one simple GPU to multiple GPU, one of the parallelism techniques integrated in vLLM is tensor parallelism. So it allows to share the weight horizontally, and instead of loading all the weight in one GPU, you can shard and improve also the latency, because vLLM does not have to load the full weight. So when the model is bigger, it cannot fit in one device, and tensor parallelism is allowing to scale and to load this large model. So vLLM provides an optimized all-reuse implementation with the data, with the input shared horizontally and all-reuse for the output. So it works well when you have less than 8 devices, which is like the classic HGX server from NVIDIA or for AMD, MI300X or Gaudi 3 for Intel. But when you want to scale after to multiple nodes, you need also to involve other parallelism techniques. It's why you can also, in addition to tensor parallelism, because you will still use multiple nodes, you will use also a pipeline parallelism. So here, you will do point-to-point communication instead of an expanding or reduce. So in this situation, we will use multiple, each GPU could take care on a certain number of layers. Meaning that we'll connect this layer and it will allow the multi-node, multi-GPU. So to implement this with vLLM, you need to use Ray. So Ray will share the communication. and you can use pipeline parallelism to share and to run on multiple nodes. So it's just pipeline parallel size, and you can mix multiple parameters. And the latest parallelism technique I'm presenting is the expert parallelism. So we are discussing a lot of mixture of experts. So instead of sharding horizontally or sharding per grouping the layers, we have a mechanism also in vLLM to allocate some specific expert models per device, per GPU. So with this technique, a token router can route specific compute to specific device. So this also can create some problem to imbalance between the experts, because the balancing could be complex. But you can mix, and a lot of recent models are provided with mix of experts. Yeah.
Okay. Now, so basically, the second part of the presentation will be mostly about quantization. So this is how a standard, like a quantization lifecycle should look like in practice. So basically, you can take two pathways when you want to deploy a quantized model. The first one is you take a model from Hugging Face Hub, you pull it through our LLM compressor, which is a library which implements state-of-the-art quantization algorithms that you can get from research papers these days, and it supports different quantization schemes. And this should be ideally a very iterative process. So you quantize the model, you evaluate, you're not satisfied with the accuracy, you do it again, and so on and so forth. Or you can go to, for example, Hugging Face Hub, like Red Hat AI Hub, which contains more than 400 state-of-the-art quantized models, and we are actively releasing all of these new models that are coming out every single day. And then, once you're satisfied with the accuracy of the quantized model, you need to benchmark the inference performance of the model, so you understand the gains that you're getting from quantization. For this specific case, I'm showcasing here the Kite LLM, which is our library for like simulating the real workloads on top of your deployment. It's compatible with vLLM, TGI, any other like OpenAI endpoint. And then here you can see how the latency looks like, how the throughput looks like under different loads. And once you're satisfied with that, you can go and deploy your model, for example, in vLLM. So basically, today, regarding quantization, I'd like to give you like three main takeaways related to quantization. So basically, quantization became a very popular topic during the last year or so, and there has been a ton of models appearing on Hugging Face Hub. And one unfortunate thing is that quantization got a lot of the bad reputation because most of these models are coming out without proper evaluations. And this creates like situations like this one here, where the user is seeing a model with, for example, FP8 quantized model having like a 5 points lower accuracy than the unquantized baseline. And this creates a lot of skepticism in the community about the adoption of the quantized models in the actual like real world deployments. So the first message here is that not all quantized models are created equal. And what I mean by this is the fact that when we are applying a specific quantization format, there is literally like a million different choices that we can make, going from which format to use, how to apply it, which algorithm to use to apply the specific quantization, whether it's a static or dynamic quantization, whether we're using calibration data or we're not using calibration data, which observers we're using, how fine-grained scales are we using one scale per tensor, per block, per channel, and so on and so forth. So there's a million different ways to do this, and this kind of inspired us to kick off a project which we called Give Me VF16 or Give Me VF, where we literally took all of the popular models in the community, going from decoder-only models to MOE models. So in the model size, we look at like anywhere from 1 to 3 billion in size, up to the MOEs like the DeepSeek, which are like 671 billion in size. And basically, we quantize all of them into 3 different formats: FP8, Int8, and Int4. And then we tuned calibration properly to get like the satisfiable accuracy recovery. And then we took all of the popular evals that exist in the community, like OpenLLM Leaderboard V1, V2, all of the popular reasoning evals, long context evals, arena hard, multimodal, and so on and so forth. In total, this was around more than a million evaluations that we did. And basically, we found the same message across all of these. And that's it, that the int8 and FP8 quantized models are, when calibration is tuned properly, they get to the accuracy recovery of 98 to 99%. So very, very easily. Whereas for int4 models, this range goes anywhere from 95 to 99% accuracy recovery, which usually depends on the size of the model. Very, very small models are usually in this range of 95, 96% recovery. And then once we go to the higher models, this becomes much, much easier. And here I'm showcasing just simple one example out of the many that we have, which covers the reasoning performance, like the most recent DeepSeek R1 still models across 3 popular reasoning tasks and the entire like Llama and Quant family. And basically the message is the same. Blue and green bars here, which represent FP8 and int8 respectively, are almost indistinguishable from the gray bars, which are like the unquantized baseline. And then the yellow bar, which represents the int4 models, usually has like a smaller drops on the smaller models like 1.5V Quen and Llama 8. So this was the first message. So not all quantized models are created equal. There is a way to tune the quantization to get the good recovery. The second message is the fact that quantization opens up additional kind of pathway for us to improve the quality of our LLM deployments. And what I mean by this is that in the academic setup, usually we are working in an environment where we are designing new quantization algorithms, and we are always looking at the accuracy recovery relative to the unquantized model. And that's like a perfect fair setup to compare different algorithms. However, in the real world, the main question that we are asking ourselves is, what is the best model that I can deploy given my deployment constraints? And usually the main deployment constraint that we have is the amount of the GPU memory that we can allocate for that application. And basically here I'm kind of cherry picking a specific example because it lends itself perfectly for this illustration, like these Quen 7B and Quen 14B models. So basically, let's say that for our deployment, we can allocate 14 gigs of the GPU memory. The best model without quantization that we can serve is the Quen 7B unquantized model, which gives us a score of 65 on these reasoning evals. However, and that's the best we can do without quantization, right? However, quantization enables us to go to the higher model, like a larger model, like a Quen 14B, which originally, like in unquantized form, takes up like 28 gigs of the GPU memory. We quantize it down to 8-bit, and then we get back to this like a 14 gigabyte of the memory GPU constraint. But now we can enjoy much better accuracy depending on which quantization format we use. So we kind of get to leverage the accuracy of the larger model. But then with quantization, even if we lose 1 or 2 percentage points relative to the unquantized model, we are still way better than the smaller unquantized checkpoint. And yeah, larger quantized is always better than smaller unquantized, at least in terms of the accuracy. And the last message here is, now when we are satisfied with the accuracy of our quantized model, the next question that we are faced with is, what is the best quantization format for my specific deployment? And for this specific purpose, I'm here showing the inter-token latency, how inter-token latency changes with respect to the number of queries per second that we are sending to our Llama 8P model on a single A6000 under some specific use case, which we call here like a doxing generation. And we are looking at 3 different quantization formats, BF16, so this is the unquantized, like a baseline model, int8 weight and activation quantized model, and int4 weight only quantized model. And basically there are like 3 main things to observe here. The first one is that when we are in the range of 4 queries per second and less, the best quantization format for this specific deployment would be int4 quantized model, because it gives us the lowest latency, right? However, once we reach the 4 queries per second and more, we are going from the memory bandwidth bound regime to a compute bound regime. And in this specific case, int4 weight only quantization is not the optimal choice for our deployment. As you can see, int8 weight and activation quantization becomes much better choice for this, and it has like a consistent improvement in the latency. And then the final piece, which probably not many of you are not probably expecting this, is the fact that once we push even more, like more queries per second, at some point we will reach a regime where int4 quantized model is performing worse than the unquantized baseline. And this is mostly because in this regime we are heavily bounded by compute, And weight-only quantization doesn't improve that part at all, because it's just going to do like loading of the quantized weights, doing the dequantization in order to produce the outputs. And then we'll be paying a very large cost for this dequantization stuff. So the last message here is that there are no golden bullets. You should know your deployment, and the way kind of to get to know your deployment is, for example, taking GuideLLM or any other library which allows you to completely automate this process. So you take your model, you deploy it, you run like automated benchmarking part, and then you get a graph like this, and then you figure out which quantization format is best for your deployment. And yeah, here are the links on where to go next. LLM compressor. Yeah, this is maybe like a good thing to highlight here. LLM compressor has been adopted by a Meta team as well. So we collaborated with a Meta team on the Llama 4 Maverick release, where they would produce like FP8 model with LLM compressor. And then here are the links for GuideLLM, RapidAI's Hub, and vLLM. That's it. Thank you.
Are there any questions?